Everything you've ever been told about quantum computers is wrong. They don't split into parallel universes. They don't run every possible answer all at once. The truth is actually quite stranger. And in late 2024, Google proved it with a chip called Willow. But to understand what Willow actually did, you've got to start with the machine already in your pocket. It's a master of illusion. Every photo, every message, every app is just a sequence of tiny switches flipping on or off, 1 or 0. For 80 years, that binary language has been the definition of a computer, and every leap forward has come down to one simple trick: making the switches smaller and cramming them closer together. We have now shrunk them to a few nanometers across, so small that physics itself starts to break down. It would seem that we're simply running out of room. But then, Google built Willow. They handed this chip a benchmark built to be brutal, a problem designed to push ordinary silicon to its breaking point. Willow cleared it in under 5 minutes. The best classical supercomputer alive would need almost 10 septillion years to match it, a span billions of times longer than the universe has ever existed. It's a pretty staggering headline, and the explanation that almost everyone gave for it is complete fiction. Here's the story I opened by calling a lie, and here is why it's so easy to believe. A normal computer checks answers one at a time, like a detective working through a filing cabinet. But a quantum computer checks all of them at once. It splits into parallel realities, runs every possible solution simultaneously, and then plucks out the winner. Infinite computing power for free. It's a pretty clean story. Tech journalists repeat it, executives repeat it, and people who know better even repeat it. But it's all false. The truth is stranger and a lot more dangerous. It all starts with the basic unit of information: the qubit. A standard bit is a switch, 0 or 1, never both, never anything in between. But a qubit breaks that rule. Before you measure it, it lives in a state called superposition. And here is where the myth takes hold. People hear both states at once and picture two calculations running side by side. But that's not quite it. A qubit doesn't hold a 0 and a 1 at the same time. What it holds is a wave. More precisely, a wave of possibilities, where every possible state carries its own probability amplitude. And this is the detail that changes everything. Those amplitudes aren't just positive percentages. They can actually be negative. They can even be complex numbers. That single fact, that probability can go negative, is the entire secret of quantum computing. Now, hold on to that for a second. Chain normal bits together, and their power grows step by step. 8 bits can represent any number from 0 to 255, but only one of those numbers at any given time. Chain qubits together, and through entanglement, the space explodes. 2 qubits don't hold 2 states, they hold a combined wave of 4. 3 qubits holds 8, string together just 300, and the system holds more possible states than there are atoms in the entire observable universe. And that number is where the hype actually lives, and it hides the catch that nobody puts in the headline. You can't actually read them. The instant you look at a quantum system, the wave collapses. Every one of those possibilities vanishes, and you're left holding a single random string of ordinary zeros and ones. Build a giant superposition, look at it, and you get noise. Pure garbage. Nothing gained whatsoever. So the real problem was never holding every answer, it's forcing the machine to hand you the right one in the microsecond the wave collapses. And that is what the negative amplitudes are for. They let you create interference. Think of noise-canceling headphones for a sec. When the peak of one wave meets the trough of another, they erase each other. A quantum algorithm is choreography at the atomic scale. It doesn't search a database, it tunes the phases of the waves so that every path leading to a wrong answer cancels itself to 0, while the paths leading to the right answer stack on top of one another louder and louder until that one solution is nearly certain. You're not actually searching 1,000 universes. You're actually sculpting an ocean of probability, so the wrong answers destroy themselves, leaving only the truth standing when you finally look. That's the magic. Not parallel worlds, just ruthless, precise cancellation. Now, this all exposes the one thing that the hype leaves out. This trick only works on a handful of problems. The rare ones with a mathematical structure you can bend into interference. For almost everything else, your email, your spreadsheets, the video that you're watching right now, A quantum computer is no faster than the phone in your hand. It isn't a better computer, it's a different kind of machine entirely. Superhuman at a tiny set of tasks, and pretty useless at everything else. And even that comes at a savage price. Qubits are absurdly fragile. One stray vibration, a flicker of temperature, a single particle of light, and the wave collapses before you're ready. It's called decoherence, and for 30 years, it was a wall that nobody could climb. Every qubit you added to make the machine stronger dragged in more noise, more errors, more ways to fall apart. You needed thousands of physical qubits just to protect a single reliable one. And this is why Willow actually matters. And it's not the septillion year number. That benchmark was theater, a problem chosen because it flatters a quantum machine and means nothing in the real world. The real breakthrough was quiet. Using an architecture called surface code, Google showed that as they added more physical qubits, the error rate went down instead of up. After 30 years, we're finally winning the war against noise. And the stakes on that war are total. The one mathematical structure quantum interference bends best is modular exponentiation, the exact math behind RSA and the public key encryption that guards the entire internet. In 1994, a mathematician named Peter Shor proved that a stable quantum computer could use it to factor enormous prime numbers and shatter that encryption in an afternoon. Your bank, your messages, military secrets. All of it sits behind math that's too tedious for silicon to crack, but trivial for quantum waves. Today's machines can't do it. They're too small, too noisy. You would need millions of clean qubits. Today, we're counting in the hundreds. But governments aren't waiting. Intelligence agencies are already running a strategy with a chilling name. Harvest now, decrypt later. They're intercepting encrypted data by the ton right now. Civilian, corporate, military, and they're locking it away in vaults that they can't even open yet. They're betting that the day a big enough quantum computer switches on, they'll feed it those files and crack 30 years of secrets in an afternoon. And yet breaking codes was never really the point. In 1981, the physicist Richard Feynman put his finger on a flaw hiding inside all of our technology. Our best computers are blind to how the universe actually runs. Nature doesn't think in binary. Down at the atomic scale, reality runs on waves, negative probabilities, and interference. Our machines are digital cartoons, trying to imitate a world that they can't really see. Reality is quantum, and our computers are not. Willow is the first real step towards a machine that stops imitating and starts speaking the native language of the universe. It doesn't escape to parallel worlds. It runs on the actual rules of reality, the ones that everything else is already made of. We spent 80 years teaching sand to mimic our logic. Now, we're building something that runs on the logic underneath everything. We just have to keep it from falling apart long enough to listen.